All right, so let me just remind you the discussion about the cache organization. It's basically how the cache is implemented. Remember what the cache was? Cache was that we have the main memory here, right? And then what we want to do is we want to bring in what we have is closer memory to our CPU, okay? And what we want to do is we want to bring the data that is accessed more frequently, okay, to this closer, nearby, faster, but more expansive memory. This is what we call a cache. And this basically what we call caching, okay? And we said that this was necessary because we had all these different memory technologies, and by using them with this caching idea, you're effectively bringing a copy of the data, okay, to closer to you so that you can access it. And remember that our metaphor for this was this library, your shelf, and your tabletop, okay. And tabletop is your basically is the one that you can access immediately, and but it can hold only like fewer pages, whereas on your shelf you can have many more pages, and the library access time is much larger, but you have but you can hold all the books that you would need to throughout your education life. Okay, so that was the idea of a cache, and when we were defining a cache, we said that we were using like the cache, or the cache can be specified by these three parameters. Okay, and B was it's the block size. Okay, block size means how many blocks, how many bytes do you copy, okay, whenever you need to bring in a data. That's the main page. And our example was that if you want to say, imagine that you need only a certain line in a page, but if you go to the photocopy to make a copy, then it works at the level of a whole page, and this is what we call as the block size. Okay, and block size is important because it supports what we call spatial locality, meaning that if you have like if you whenever you have you need access to data that's nearby, then it means that all the rest of the data is already in. And then we had E. Okay, E was the number of lines per set. And let me just talk before we talk about this line. Okay, this is what we call a line. Okay, a line consists of this block of data. Okay, along with the block of data, we also store some portion of the address, which we call the tag. So this is a portion of the address. Okay, we discuss why with it. And plus, we need this valid bit, which indicates whether this data is valid or not. And we call this whole thing as a line. And what we call as a set was it contains multiple lines. And the reason why we group our lines into the multiple multiple lines into a set, it was to make the search much easier and cheaper. And remember our example again that when you're getting these photocopied pages from the books, okay, and what we also when we are searching whether a certain page is in our cache or not, but one thing that we can do is we can group them into two sets, say odd number pages with odd numbers and pages with even numbers. Okay, so in this case we have two sets, and what you do is we just you can imagine these as folders that you can just put in your photocopied pages into them. And whenever a request comes, and you can check its page number. If it's odd, then you check this folder. If it's even, then you check this folder. Okay. And what you do is you get the address, and then you try to match the address with the tag. And if it's in there, then it's basically like then you can immediately get it from the cache. Else, you have to go to the previous level. Okay, so that was basically our idea, and then the last thing that we had was S, which was the number of sets. Okay, in the cache. And hence the cache size is basically number of block size times number of lines per set and number of sets in the cache. And this tells you the bytes, and this only includes like it's only the data bytes. It's not all the bytes stored in this, okay? So here is how it would work. Let's say that I have a cache, okay? I have a cache, and in this basically cache, then we have these 2 to the power s sets, okay? And let's see if I can, no, okay. And with this, then I can, like, depending on my block size, we say that if its block size is b and that's 2 to the power b, then I would set aside the b bits as my block offset because it will tell me where my data is, okay? And for example, in this particular line here, okay, this I may have like a 2 to the power b bytes here, and depending on which one do I want this first, this this byte here, or do I want this one? This is specified by these b bits, okay? And then by looking at how many sets do I have, which is 2 to the power s, then I set these s bits as my set index, which will tell me which set I should be looking into. In our example of even and odd, the s bits is actually 1. You're just looking at one bit. If it's 0, you look at the, say, even one. If it's 1, you look at the odd one. And then the rest of the address, okay, is then specified as the tag, right? So we looked at our first example, which is a direct mapped cache. In this case, E is 1. This means that I have one line, okay, per set, okay? And what we do is, let's say the cache block size is 8 bytes. If it's 8 bytes, this means that 2 to the power 3, okay? It means that I need to use 3 bits of the address as my block offset, okay? And then, then I can see, how many sets do I have? I have 2 to the power s sets. So this s tells me, so I can look at here, s bits. I use them to basically find which set I should be looking into. Okay, that's how it works. And once I do this, let me see, yes, okay. Then what I do is, once I find the set, so this is the particular set, if my, if the cached data is, if the data that I'm looking for is in the cache, then it can only be in here, okay? And what I do is then I take the remaining of the address, I compare this with the tag, okay? And also I check whether this particular line is valid or not. If it's valid, and if this tag matches the address, then it means that yes, it's a hit. We call this a cache hit, okay? This is like, you want to look for a certain page on your desk, okay? And you see that it's already on your page, okay? On the desk. And once it's a hit, then we check, we use the block offset to see, which, where my data is located. So let's say that I am just, for example, like the address that I'm looking for is 1000, okay? And in here, remember that the block size was 8 bytes, okay? So it means that now the block offset is here. So it means that the data, like if it's a jar, maybe I'll just need this data. If it's an integer, for example, then I may need these 4 bytes here, okay? But this block offset allows me to, because if this block offset was, for example, 0000, okay, then I would have gotten this data into basically from the cache. And basically, if, let me see, if in this case, if there's a no match, and meaning that, this tag, okay, is not equal to t, okay, or the valid is 0, okay, then it's a no match. No match means this is called a cache miss, Okay. Then what we do is we remove this line. Okay, we remove this line. Okay, and replace it with the new one. So we go to the main memory. We take a copy of this and we write it on top of this. Okay, that's how you're essentially copying the page. In the case of your the tabletop, you realize that that particular page is not what you're looking for. Then you go to the main memory, you take a copy, and you keep the other one, and then you put the new one on your table. Okay, so we have covered this direct map cache simulation last time, and I will then continue from here. Okay, so depending on E, okay, which is, remember again, this was the number of lines per set. If it's 2, for example, it means we have 2 lines per set, okay? And what this means is, remember this, if this is your folder, okay, you have 2 pages in the folder. It can hold 2 pages, okay? And we call this an E-way set associative cache, where E is 2, okay? And in this example, again, like we said, if we say that the cache block size is 8 bytes, then I have these 3 bits, okay, which is 2 to the power 3, as my block offset. Okay, and then depending on the number of sets and which set, well, let's say that I have 2 to the power s bits, 2 to the power s sets. So that means I use the s bits here. Okay, and which will tell me which set I should be looking for. And when I get in here, you can see that in this particular set, okay, this is where I expect to find my data. But I have 2 possibilities, either this or this. So what I do is I take these tag bits, okay, and then I then try to compare them with these 2 tags in the set. And if I have a match, then you get the data. If you don't have a match, then we have to replace that with something. We have to go to the main memory and then replace that with what we have here. Okay, and the nice thing here in this 2-way set associative cache is we are making 2 tag comparisons. So this is basically again how it works. You look at basically the tag bits and you compare this with these 2, okay? And let's say that there's a match here. So it means that I have a cache hit, okay? Then I use this block offset and then get the data. And so in this case, for example, if I am getting a short int, which is 2 bytes, then it means that my data is in here. Okay. If there is no match, meaning that my tag did not match, then one of the lines, and it doesn't for the time being, that's just pick random. One of the tags is selected for eviction. That means that you want to kick off. Okay, and then you replace it. Okay, and there are different replacement policies which we will see later, like random or least recently used, and etc. We will discuss this later. Okay.